Okay, so how about for your um, YCP? What is this YCP here? So YCP class is the location of your center of pressure. What is the center of pressure? This is class the point where your force is acting. Okay, that is where your force is acting. So we have to determine it. So what's the location of center of pressure? Now I have here um, a picture. Okay, um, let me show you this one. There, can you see it? This one, there. So this picture shows the location of your center of gravity as well as your center of pressure. What can you observe? They are just in line. So if this is your center of gravity, the center of pressure is just below that point. Okay? But in this case, our body is inclined, so of course the positions also are inclined. So as you can see here, this H here refers to your distance from the free surface to your center of gravity. Excuse me. There. And your Y sub P, that is the location of your center of pressure from the free surface to your center of pressure. Okay? There. And how are we going to solve for that? So, according to our lecture, to solve for our um, location of center of pressure, so we have here the formula YCP equals ICG over YCG times area plus YCG. Recall, YCG class is similar to HCG, or your location of your center of gravity. Your ICG is the inertia. Take note, inertia of the area about its center of gravity. Now, how are we going to solve for that? It still depends, class, on the shape of your um, container or your storage. So if it is rectangular, your ICG is solved by BH cube all over 12. But if it is triangular, you'll have BH cube over 36. And for um, circle, pi d to the fourth over 64. Okay? So depends. It depends on the shape. But of course, class, there are lots of shapes that are used, but these are common: rectangular, triangle, and circle. But there are, in reality, um, it could be a combination of rectangle and circle, or it could be triangle and square. So there are problems that it is combined. So you have to check really the formula that you are going to use there. So again, class, these formulas here are used for your forces exerted on a flat or a plane area. Now, how about for the force exerted by a liquid on a curved surface? So take note that they are different. It's because flat or plane, okay, iba-iba yung forces, of course, that are felt on that area. Pag curved naman, we have here horizontal component and the vertical component. If you could recall, force class is a vector, which means that it has direction as well as magnitude. So we can express our force into horizontal component and vertical component. And in this case, for us to determine the force exerted on a curved surface, so to determine the horizontal component, it is just equal, take note, equal to the normal force. In your physics, if you could recall, what is a normal force? Normal force class is when you have your, um, for example, you have your body there, right? For example, you have um, a box. It's like this. Let us see. Okay, wait lang. This one. Okay. Let's say I have here this body. Okay? So we have here the body, and then let's say that this body is standing, or it is placed here in this surface. So since this body here has a weight, so of course, according to our action reactions, a law of motion, so there will also an upward force, right? And that upward force refers to your normal force. So if your weight is towards the downside, or the direction is downward, so your normal force is upward. So it is the upward force that we are trying to solve here. And that upward force or normal force is your equivalent to your horizontal component of your force in that curved surface. Now, um, how about for your, what is this? Vertical component. Now, vertical component here is equal to the weight of the volume of liquid above the area, real or imaginary. So whatever the weight of that fluid or that liquid, okay, weight of the volume, it refers to your vertical components. So once you know the horizontal and the vertical component, then you can now express your force. And again, that force is only for curved surface. Okay? So that's it. That's it for the force for the curved surface.